So welcome everyone to this colloquium by Chris Moore. It's a great pleasure to have Chris Moore giving the colloquium here today. It's something we have been trying actually since, I don't know, it's been 3 years now. And there was a time when we were trying to get him over here to Stockholm. And then, lots of things happened, and then Corona and so on. But anyway, we have the pleasure to hear him now, and we hope that you will visit us sometime. So, Chris, to give you a brief biography, Chris received his bachelor's, BA in physics and mathematics, as well as in integrated science at Northwestern University, and his PhD in physics at Cornell. And for 12 years, he was, from 2000 to 2012, he was at the University of New Mexico. And since then, he as faculty. And then, since then, he's been faculty at the Santa Fe Institute at Santa Fe. And he has also held several visiting positions in France and other places. And he has written several papers, 160, from what you sent us, Chris. And then we're on several, and I know that his interests are very varied, from quantum computation to very computer science-like problems like constraint satisfaction. And in fact, constraint satisfaction problems are the area which one of the Nobel laureates who got the Nobel Prize in 2021, Giorgio Parisi, some of his techniques and his, the techniques he has developed can be used in that field. But he's also interested in phase transitions and Bayesian inference, and I guess his talk today will be more on that. He's a member of, he's an elected fellow of the American Physical Society, the American Mathematical Society, and he's also written a book, The Nature of Computation, with the Oxford University Press. And so all those were facts, but to give you some interesting, one more interesting detail about Chris, that he really likes Tolkien and Lord of the Rings. And for a very long time, the signature of his email used to be this very famous quote from Tolkien, which said something about, if more people liked food and cheer and song, rather than hoarded gold, the world would be a merrier place. Okay, on which note, over to you, Chris.
Okay, that takes me back. Thank you very much, Supriya. And I do wish I was with you physically. I haven't been to Stockholm in many years, and it's a beautiful city. You should all come visit me in Santa Fe. In between pandemics, is a great time to travel. And indeed, several of the collaborators that are here on my screen are children or grandchildren academically of Giorgio Parisi, the recent Nobel laureate. And one of the reasons I love this area is that there is a real interaction between physics, computer science, mathematics, and different people work at multiple places along the spectrum, from physics calculations to mathematical proofs and experimental work. So it's a very vibrant interdisciplinary area. So I'm going to talk to you about an analogy between statistical inference and statistical physics. You may be familiar with this analogy, but I'll try to give a quick introduction for it if you're not. And the goal is that we want to understand how to find patterns in noisy data. And the short version is that patterns in noisy data act a lot like thermal equilibrium at non-zero temperature. And so the question is, what techniques and ideas can we import from statistical physics into this field, variously called data science, machine learning, or statistical inference? And one thing we'll find is that there are phase transitions where, just as in physics, there can be a critical temperature at which point the system loses a lot of its order. There can be phase transitions in Bayesian inference where, if the system is too noisy or the data is too sparse, that suddenly we can no longer find the patterns in it. We can no longer detect the, quote, ground truth. And so once you know that these transitions exist, then there's an algorithmic question of, can we actually efficiently, computationally achieve inference all the way up to that point? Or are there barriers, which, as we'll see, are like those in glassy materials, those are barriers to reaching equilibrium. Those might correspond to barriers for an algorithm finding the correct answer. And that will lead us to two different kinds of transitions, one where there's simply not enough information in the data to do the job, and the other where the information is there, but it becomes computationally very difficult, we believe, to do the job. So here is a very brief introduction to this analogy. Why in the world would anyone fit a straight line to a set of points by minimizing the sum of the squares? Why do we do this all the time, right? So we have a model of ax plus b, and we want to choose the parameters of this model, the slope and the intercept. Well, very often we do this by minimizing the sum of squares. Well, there are lots of different reasons to do this, but one of them is that we believe that the actual way the data is generated, the way it comes to us from nature, is that there's that straight line model plus some kind of noise. Specifically, if that noise is Gaussian, then the total probability of that data is exponential in that sum of squares. And then what some people call the maximum likelihood estimate, but we call the ground state, is the line which minimizes that energy if you associate the energy with minus the log probability. And of course, we should associate the energy with minus the log probability because Boltzmann taught us that, that the probability of a state is exponential in its, in its energy with a temperature parameter. But there's this also this nice analogy which I learned from a good high school teacher of mine, which is that minimizing the sum of the squares is the same as minimizing the energy of a bunch of springs that are connecting the data point to the straight line. She actually took a yardstick and attached rubber bands to a bunch of thumbtacks and said, "Look, there's the least squares fit." So, but the next question is, if the maximum likelihood estimate is the ground state of this system, well, then there's an issue which statisticians have wondered about for a long time. I mean, we don't want to claim that we're certain about our estimates, right? That would be like saying that we're at absolute zero. And so now there's this connection between Boltzmann and Bayes. So Reverend Bayes says, never just give an estimate of your parameters. You should always tell us something about how uncertain you are about those parameters. Every statistician agrees upon that. The question is, how do we best express that uncertainty? Now in physics, we often do this using error bounds, and we do this using an attitude called frequentism, where we say, well, it's very unlikely that it's outside these bounds. Reverend Bayes said something a little different. He said, I want the entire posterior distribution of the parameters, if possible. So just as the thermal equilibrium distribution, the Boltzmann distribution has this form where at very low temperature, it's concentrated on ground states, and at very high temperature, it's essentially uniform over all possible states. And so we can equate the temperature to some measure of noise, or in this case, the looseness or jiggliness of these springs. This gives us an energy, a Hamiltonian, where the space of the model is the parameters that we are trying to fit, such as the slope and intercept, and then there's some equilibrium distribution. And so Bayes would say, well, this is the posterior distribution of these parameters given the data. Okay, so that's the whole analogy, and actually, if you look at the terms used in machine learning, they talk about Gibbs sampling the same way statistical physicists talk about Gibbs sampling, and when we talk about the free energy, they're always talking about the Kullback-Leibler divergence and so on. But as you probably know, a lot of thermodynamics is just information theory in disguise, and a lot of statistics is just thermodynamics in disguise. Now, let's look at one of the classical systems where there's a phase transition, the Ising model of magnetism. Things interact with their neighbors in a simple ferromagnet, unlike a spin glass. Each atom wants to be lined up with its neighbors. So the energy is essentially the number of disagreements between neighbors. And as you know, when the interactions are strong enough or the temperature is low enough in a macroscopic system, a lot of atoms line up together and we get a macroscopic field. And by the way, I learned that this general fact that magnets get weaker when they get hotter was known all the way to the ancient Greeks and Chinese and Babylonians. But it wasn't until Curie that we learned that there's actually a sharp transition where rather than the field going down gently to zero until the whole thing melts or something, instead it drops precipitously to zero. And of course, what it looks like microscopically is this, that above that critical temperature, the up and down state of the atoms is essentially white noise. But below that critical temperature, there's, with probability tending to 1 as the system gets larger, there's an unequivocal majority with little islands of the minority state. Okay, so that's probably nothing new to you, but now I want to draw this analogy to problems in data and inference. So for instance, suppose that we have a bunch of points in a high dimensional space, and we're trying to cluster them because we believe they belong to 2 distinct clusters. Well, you can imagine various parameters which would take the place of the temperature. One might be the width of these clusters, the noise. Perhaps each one is a center plus Gaussian noise. So one issue is the width of the clusters relative to the distance between them. As that goes up, then the system, in a sense, gets hotter. Another, it turns out, is the ratio of the number of dimensions to the number of points, or, well, the inverse of that would be the inverse temperature. So one of the reasons why high dimensional statistical inference is challenging is that, we often say, oh, there's big data, there's a ton of data. Well, yes, but on the other hand, in many cases, we're trying to infer many different things about these data points. What group they belong to, or what cluster they belong to. And relative to the number of different things we're trying to learn, there's actually not so much data. So for instance, in a social network where each person only has a few strong connections, actual friends, then relative to the number of points, there's actually not so much data, even if the network overall is huge. And this is this regime of so-called high dimensional statistics, which is where many modern data sets lie. So anyway, what I want you to imagine is that as we vary one of these parameters, the noise or the dimensionality, there could be a transition where on one side, we can correctly label most of the points, say 80% of the points, just as at certain temperatures, 80% of the atoms of a magnet are aligned. Whereas on the other side, it might really become white noise, where asymptotically, we could do no better than flipping coins in figuring out which of the 2 clusters points could live in. All right, so that's the overall idea. And now let's turn to this very popular question in network science. So this is from a 2004 paper from an election a few rounds ago in the United States, where each node is a blog. And then, because we are social primates, we tend to link up mainly to those who agree with us. It's one of our faults, or depending. And so based just on the topology of the network, it's a fun thing to do to try to figure out which blogs were Democratic and which Republican, or vice versa, with a couple of greens thrown in. So in this particular network, the structure is very strong. So the problem is very easy. There are many algorithms which get this correct in 97% accuracy. But there are other cases where it's not so clear. So here is a lovely example. A friend comes to you and says, I have this network, I've measured the interactions between some things. Could you please find 2 communities for me? where the connections are mostly within communities instead of between communities, kind of a ferromagnetic model. And so you run a little algorithm and you say, I've done it. I have found you a division into two communities where only 11% of the edges cross between the two, and the other 89% are all within the two communities. Well, clearly we found something, let's publish. But then you run your algorithm again from a different initial state or something like that, and you find another state, another way of labeling dividing the nodes into two groups. Here I kept the colors of the original grouping the same, and now the location is based on the second grouping. This one also only has 11% of the edges crossing between the two groups. And it might even have one less edge crossing between the two groups. It might be slightly better than the first division, but you can see from the colors that it's completely uncorrelated from the first division. So then which one is correct? What should we publish? Well, actually, this is all just a lie, because this graph, this network, is actually completely random and doesn't actually have communities at all. What I did was I gave each node 3 neighbors, but I wired them up to each other in a uniformly random way. So what's going on here is that, and this is again a consequence of kind of the high dimensional nature of this problem, well, there are roughly 2 to the n ways to divide it into two groups. That's exponentially many. And out of those, there are a lot, in fact, which appear to be very good, which by chance have a surprisingly small number of edges between the two communities. So you have many convincing looking divisions into two communities. And I got into this business because many off-the-shelf software packages for exactly this problem, for clustering and visualization in networks, produce things like this without any indication of how certain or uncertain they are, or any indication of what other competing results they could have gotten. Well, so this is a classic issue in statistics. What's happening is overfitting. We found not just one, but many illusory community structures when there wasn't actually any at all. And it's this classic problem where when you have data, it is tempting to fit a fancy model to the data. In that case, a model with communities. In this case, a model with an 11th degree polynomial, which tells you that this time series is about to go up and you should buy this stock immediately. But in fact, it's fit better by a low degree polynomial, which does a worse job of fitting the data we have, but a better job of fitting the data that we don't have yet. So this is something that, statisticians have been telling us about for a century. I think it's pretty well understood in the physics community. But if you look at papers in other fields, I think sometimes there isn't enough understanding that the temptations of fitting data with the fancy model are too great. And when you do that, you often see things that are not there. Black cats in dark rooms, even when they're not there, as they say. Anyway, so how do we solve this overfitting problem in networks? How do we do this right? And I think the right way to do this is with ideas from physics. So rather than trying to find the ground state, the optimum, the maximum likelihood estimator, the single best fit of these community divisions to the data, we should look at the entire landscape of models. In physics, the entire energy landscape; in Bayesian terms, the entire posterior. If there really is structure in the data, then this landscape will look kind of like this, like Mount Fuji. There'll be one point, or at least a small region of similar points, which have higher probability or lower energy. And every point which is almost as good as that optimum will also be close to that optimum. Okay. So in this sense, if you sample from the posterior or from the equilibrium distribution, there will be a lot of consensus between those samples. On the other hand, if it's more like this, more like a spin glass model, there will be many competing local optima, which are almost all as good as each other. but which are very far from each other in the space, very little correlation. And in that case, you could ask, gee, is this the right model for the data? And there's an interesting tension here between what we do with our models, right? In physics, we want to understand this landscape. It is what it is. We want to understand it as best we can. But in inference, if I have a type of model where it gives you this just sort of uninformative glassiness, well, as a scientist, you might say, oh, well, this is the wrong model for the data. And you might throw out the entire type of model and instead look for a model where the landscape is more like the left, because your goal is to find the structure in the data. So anyway, one example I like to give is that if there are many ways to build a rocket and one is a little bit better than the others, you should probably do that. You're designing something. But if what you're trying to do is learn something about nature and there are many competing models and one is only slightly better than the others, then maybe you're just barking up the wrong tree. Maybe you're just missing the point and you should look for a different type of structure. Good. And finding the optimum might be hard anyway, right? So not only is the optimum difficult to find, but it might be misleading even if you could find it. All right, so now let me tell you about a specific model of networks with communities, which we might try this approach on. It's called the stochastic block model. It actually goes back first to the sociology community, although many communities, including physics and computer science, have rediscovered it over the years. In this model, each node, each vertex, has one of k labels on it. They belong to k different groups. And then there's some matrix of connection probabilities where their probability that there's a link between a particular node I and a particular node J is P sub RS if node I belongs to group R and node J belongs to group S. Okay, so in this case with three groups, we would have a little 3x3 matrix, which tells us the probability of within group connections, between group connections, where the phase transitions live, and where this problem is intuitively challenging is when the network is rather sparse. So if these probabilities scale as 1 over n, where n is the total size of the network, then on average, each node only has some constant number of neighbors. A popular special case is where there's one density of connections within groups and another density of connections between groups. And typically we think of it as more likely to connect to others within your group, which is a kind of a ferromagnetic model. Some people call it homophilic or assortative. So now that we have this is what we call a generative model. It takes the hidden data, the things that we're trying to infer, in this case, the labels of the nodes, the group memberships, and it generates a fictional data set, namely a network. But now we have to try to invert this. We're given a network and we want to try to find these labels using this statistical physics notion. So we're going to do this by defining a Hamiltonian. So again, Boltzmann taught us that, at least if the temperature is 1, that the energy is minus the log of the probability. Well, we've been given the probability of the network conditional on the labels. It's what we just said in English. Their edges exist with probability given by this matrix. And so the probability of getting the network is just the product over all the edges that do exist and the product over all the edges that don't exist of the probability that those edges do and those edges don't. So it's easy to write that down. Of course, the challenge is inverting this and getting the probability of the labelings, if you will, the spin state given the network. Anyway, to turn this into a Hamiltonian, we take minus the log, and now it's a sum of pairwise terms. And now you note, if you're familiar with the Ising model and the Potts model and these other models that are favorite models of statistical physics, you say, oh, well, this is starting to look familiar. The first term in that sum is a sum over all pairs of nodes that have an edge between them of minus the log of the probability that they would if this were the right model. And so if that probability is higher, if they were in the same group, then this is just a ferromagnetic interaction term. The second term looks a little bit stranger. It's a set of interactions between all pairs that do not have an edge between them. On the other hand, it's rather weak because if P is order 1 over n, then log of minus 1 over P is also order 1 over n. So the second term becomes a very weak kind of global antiferromagnetic interaction. And what it's doing is making sure that we don't just lump everything in one group together. In other words, what it will do is it will encourage states where we have large clumps of several different groups that are less connected to each other. Okay, but so at this point, this is a Hamiltonian, it's a spin system, and now we can ask, what is its physics? Okay, so now there are many ways to study the physics of spin systems. You know, we do Monte Carlo calculations, for instance, but because I hang out with children and grandchildren of Giorgio Parisi and, you know, descendants of Hans Bethe and so on, I like this thing called the cavity method, and which in fact computer scientists independently discovered and called belief propagation. So we often think of it as a way of doing self-consistent calculations where we imagine, okay, if there were a hole in this part of the crystal instead of an atom, then the other atoms, its neighboring atoms, would cause a field in that hole. And if we put the atom in, then it would cause fields on its neighbors. And then we want everything to be self-consistent and we can calculate something. But we can also treat this as an algorithmic idea to run on specific networks handed to us by our sociologist or biologist friends. And so in this context, it works like this. Each node, each atom or vertex, sends a message to each of its neighbors, which you can think of as a field. But the interesting thing is that, so what does this message say? So I, which means I, tell you, J, my current estimate of the probability that I belong to group 1 or group 2 or group 3. But there's a clever twist, which is that when I send you my estimate, I base that only on the messages I'm receiving from my neighbors other than you. Okay. And when I talk to them, I take your message to me into account, but not their message to me into account. This turns out to be the right analogy with the classic cavity method. There are simpler mean field methods where we take everyone's message into account and send everyone out the same field. But this is really the right way to do it because it imagines each person's influence on their neighbors as if that neighbor were not there, as if that neighbor were the hole in the crystal. It also intuitively avoids a kind of silly echo chamber of information where, you know, I tell you a rumor, you reflect that rumor back to me, I amplify it and send it back to you, and so on. And so it brings, as you wish, fresh information into the conversation. At this point, I usually tell a joke about American talk radio. Okay, so we update these messages, passing them back and forth, updating them with what is essentially Bayes' rule until it converges. When it does converge, if it does converge, it gives us several things. It gives us an estimate of the free energy called the beta free energy. It also gives us estimates of these marginal distributions, the actual probability that each node belongs to different groups. This may be accurate, it may be wildly inaccurate, but you know, sometimes it works. Okay, I'm going to kind of flip through this, except to tell you, I mean, this is a very rude equation. It's rude for me to describe it 8 in the morning and for you to try to read at 3:30 in the afternoon. We're both sleepy for different reasons, but it's a product of a sum. And it does make an important assumption, which we also make in the cavity method in spin glass theory, which is we assume that my different neighbors who are talking to me are independent of each other. Okay, this is the mean field assumption. Strictly speaking, it's independent conditioned on my state, but I'm assuming that they do not interact directly with each other, but that they only interact through me, right? Just like when we do mean field calculations, we ignore a lot of the lattice structure and so on, and in particular, we ignore short loops. As a result, this technique is only exact on trees. And in graphs that have a lot of short loops, in networks that, social networks have lots of short loops, so do lattices, this is going to be wrong by a certain amount. And so that's something that we're going to have to watch out for. Okay, so since I want to finish soon, let me show you some numerical results from a physics paper that Lenkos Deborova and Florent Khrushakala and their PhD student at the time, Aurélien Dessel, and I wrote a little while ago. And here you show a measure of accuracy or magnetization as a function of, how much are nodes willing to connect with those outside their group versus inside their group. And what you see is this sharp drop, a lot like in the magnetization of the Ising model I showed you 20 minutes ago. So it looks as if, as a temperature-like parameter, which is this ratio between out-group connections versus in-group connections, as that increases, you see this sudden drop where, as it passes a certain critical value, we do no better than chance. The magnetization, if you will, drops to zero. Below that point, when the structure is stronger, the temperature is lower, we can find the communities with high accuracy. Now, my friends said, oh, but belief propagation, or the cavity method, is the Bayesian optimal thing to do in sparse random graphs. I was like, wait, really? And they were like, yes, let's conjecture in this paper that not only does belief propagation fail in this undetectable region, but that no algorithm can succeed. That this is not a fact about this algorithm, not a fact about this method. It's a fundamental fact about this inference problem, our ability to find these communities. Okay, so they convinced me. And you can calculate this threshold, and I'll tell you how in a moment. Here's how. There is a stupid fixed point of this belief propagation when the parameters are symmetric, the groups are of equal size, and so on. That stupid fixed point says, oh, I'm equally likely to be in each of the 3 groups or each of the 7 groups or whatever. What about you? Well, if everyone tells you that they're equally likely to be in each of those groups, you do the math and you say, oh, gee, I'm also equally likely. So what happens is everyone essentially sets their field to 0 so that their marginal distribution, their local equilibrium distribution, is uniform. So, and then by symmetry, that's a fixed point. Well, the question is this fixed point stable? And what's happening in this graph at that transition is something which statistical physicists sometimes call the Keston-Stigam transition or the Kosterlitz-Thallis transition. It becomes stable, and in fact, when there's a small number of groups, it becomes globally stable. So even if you seeded belief propagation with some initial correct information, it just goes away, and we end up learning nothing at all. So we conjectured this in a physical review paper, and then a couple of years later, some very smart friends of ours in combinatorics and random graph theory probability proved that yes, in this undetectable regime, there is in fact not enough information in a rigorous sense in the network to find the nodes, to find the labels better than chance, asymptotically as n goes to infinity. There is not even enough information to convincingly distinguish this network from a purely random graph, what people call an Erdős-Rényi random graph, where there are no communities at all, and everyone is equally likely to connect to everyone else. Okay, so this is a real information theoretic transition. It's a real thermodynamic transition. Even if there were no computational issues and you could really sample from the equilibrium distribution, in other words, if you could really do Bayesian inference, you still couldn't find the communities. So for two groups, I've sort of flipped around the axes here. Here, lambda is an eigenvalue, which has to do with the strength of the community structure, an eigenvalue of a little transfer matrix. The problem is either easy, belief propagation works, there are spectral algorithms that work, or it's impossible. There's nothing you can do. So that was a very nice result, and a kind of good cautionary tale for people who look for communities and networks, that they might not be able to find them, and that the communities they are finding might be fictional. There's a lovely version of this, which goes back to probability theory, which has to do with rabbits. So, as you know, rabbits reproduce asexually. There is an ancestor rabbit. It is of one particular color. That's like belonging to one of our two communities. Each time it has a child, with probability lambda, which is that same eigenvalue I mentioned before, the child inherits its color. With probability 1 minus lambda, the child's color is a random coin flip. Okay, might be the same as the parent, might not, but the information is not transmitted. And then many generations later, we ask, is it possible from the population, many generations later, to infer the color of the ancestor rabbit better than chance? Well, it turns out there's a phase transition here too, and it's maybe not where you expect. It depends on the average number of children. But for instance, you might think that even if the chances of the child having the same color as the parent are 60%, you might think that that's already enough, but it's not. It turns out that as we go down the generations, that information gets washed out by the noise. So the threshold for inheritance has to be better than a half. What's the metaphor here? Well, the ancestor is some central node that we're trying to figure out what group it belongs to, what color it is. Its neighbors are its children, its next nearest neighbors are its grandchildren, and its descendants are the nodes in some sphere in the network far away from it. So what this theorem says is that even if I generously told you the true labels of all of those, you still would not be able to figure out the label of the central one better than a coin flip asymptotically. So that's one of the tools they use to turn our conjecture into a proof. Now, I just want to briefly say that there are other regimes. There's a fascinating regime which happens in many of these inference problems, where inference is information theoretically possible, but computationally hard. And this is because there's a first order phase transition. So again, a tight connection between the physics phenomena and the algorithmic phenomena. This is kind of a busy graph, but what's happening here is that if I run belief propagation, then the accuracy I achieve depends on where I started. So you see that green line at the top. I'm sorry, I don't have a pointer. I thought I had a pointer, but I don't. You see that green line at the top. That's a high accuracy fixed point. We reach that point if we start fairly close to the truth. But unfortunately, we have to start quite close to the truth, and this is an exponentially large space, and so that hardly ever happens. If we start with random initial guesses for our messages in the belief propagation algorithm, almost always we converge to the blue line at the bottom, where we do no better than chance. So what's happening here is a phenomenon familiar from spin glasses, and I'll skip over to this. You know, window glass, as we know, its lowest energy state, silicon dioxide, its lowest energy state is perfectly crystalline. But that state has a very small basin of attraction. And if we start from melted glass and cool it down for less than the age of the universe, it will not get over this energy barrier. And it will never find that crystalline state. And it will stay in this amorphous state, this glassy state, until the stars burn out. Well, this is a similar situation. So the correct state is hidden behind a free energy barrier or a probability barrier. And if you did, for instance, a Monte Carlo experiment, it would take exponential time for it to go from an unmagnetized state, an inaccurate state, to an accurate one. If you're very lucky and you start out close to that accurate one, you will find it. And it has higher probability, lower free energy. So you can tell that you found it. But its basin of attraction is very small. And so you would need some clear push toward that state to get into it. So in this situation, if you could magically do Bayesian inference and magically sample from the posterior, you would do well. You would reach those accurate states. But algorithmically, that's very difficult, both for the molten glass and for you, right? The molten glass is trying to find its low energy state. You're trying to find the high probability state. Both of you will get stuck for exponential time, we believe. Now, this has to do with these grand conjectures in computer science, the P versus NP problem and so on. There could be some magical algorithmic way to tunnel through or jump over this energy barrier, but we really don't think so. So we believe that in this regime, no algorithm can work in less than exponential time. So that's a lovely story, I think, about how some physical systems cannot reach equilibrium and some inference problems are algorithmically hard for the same reason. So I know I should finish up here so we have time for some questions. I'll just say that what happens in this network setting is that when you have 4 or more groups, you now have this middle range, which is information theoretically possible, but computationally hard, as well as an impossible region on one side and an easy region on the other side. We now have this curious middle ground. And it turns out this happens in many problems, including high-dimensional clustering. If I had more time, I would tell you about other things. I would tell you about what if I do give you for free the true labels of a certain fraction of nodes? Well, if I give you enough of those, then suddenly you jump over into that small basin of attraction, and then you achieve a high accuracy. And this produces a very pretty two-dimensional phase diagram in both the overall temperature and the number of nodes I give you for free. It becomes, giving you that free information is like a local field that pushes you toward the truth. If I might tell you that if we are not sure how strong the structure is, then there can be a spin glass phase where we're looking too hard for structure that isn't there. And when you do that, the belief propagation stops converging because it's kind of jumping around on that very bumpy landscape. And so that spin glass phase, SG there, is a physics version of you're overfitting, you're looking harder for structure. Physically, you're operating at too low a temperature. And so you're focusing too hard on the ground states rather than the overall equilibrium distribution. I could tell you about hierarchical clustering, dividing things into communities and subcommunities and making this very pretty picture. I could tell you about a spectral clustering method based on the non-backtracking matrix, which is like a random walk which never goes back to places it just was, which produces this very pretty spectrum in the complex plane. And I could tell you some other things that I don't have time to tell you, like if we're trying to find structure in tensors rather than in matrices, then we have 3-way interactions and more-way interactions, and that we get to talk about this obscure thing called the Kikuchi hierarchy, which is essentially like cluster expansions with more and more nodes. And then I would just tell you my morals and my conclusion slide. So many problems in inference involving noisy high-dimensional data have phase transitions. And these include not just these popular things in networks, but many things that people are interested in, for instance, medical algorithms for MRI imaging, compressed sensing, looking for low-rank structure in noisy matrices and noisy tensors, high-dimensional clustering, and so on. Ideas from physics can help us locate these transitions and even sometimes inspire new algorithms which are optimal in the sense that they work all the way up to those transitions. If you like proofs, some of this work can be made mathematically rigorous, and that's a very interesting boundary right now. And also, just a note about culture, right? If you hang out with machine learning people, you know that they're scientists, but they're also engineers. They have a big data set. They want to do the best job they can. They're willing to throw any tool at that problem. And as a result, they often say, well, last year we used a 6-cylinder engine, and this year we're using an 8-cylinder engine, and we're using a Phillips head screwdriver, and we're walking around it twice counterclockwise and then kicking it. And now look, we got a higher accuracy. And it can be hard scientifically to understand, well, gee, what's really going on here? What are the strengths and weaknesses of these techniques? What kind of data do they work on? What kind of data do they not work on? What kind of mistakes do they make? And because I was raised as a physicist, I prefer this attitude that as we should use simple models and simple algorithms whenever we can, partly because, as you've seen, we can achieve some analytic understanding of when they work and when they don't. So that's all I have to say. Thank you very much.
Thank you, Chris. That was really fascinating, and it looks like we'll just have to invite you back here to tell us about all those things that you didn't get time to tell us today. But next time in person, I hope.
Absolutely.
Well, so questions, anyone? Let me see. I'm looking at the participants as well as if anyone's raised any hands and stuff. Yes, Eric?
Yeah, I don't have a question. Just say thanks. It was a very nice talk. I have to leave now. Hope to see you soon again.
Thank you for joining us.
It was a great pleasure.
Hope to see you too.
Yeah.
Okay, so any questions, anyone? Maybe I can start it off. I mean, I had several questions actually. One was just, something that I've just wondered about a bit. This belief propagation algorithm, when was, you said computer scientists, of course, it was known before all the spin glass community got into it. So when was it used in computer science? When was it?
So in computer science, people credit it to Judea Pearl.
Okay.
And so, I guess the question of priority sort of depends on what you count. But it was certainly independent. So, computer scientists talk about graphical models where there's a bunch of variables, there are a bunch of interactions between variables. They call those interactions probability weights, but they really are just like the terms of a Hamiltonian. So this idea of sending messages to neighboring nodes, it appeared as what people call a variational method, where that the actual distribution, equilibrium or posterior, is this very exponentially complicated high-dimensional thing. But maybe you could learn something by approximating it by some simpler family of excuse me, I have the hiccups. Maybe you could learn something by approximating it with some simpler distributions. So you choose some simpler family of distributions, and then in our terms, you minimize the free energy within that family, which in their terms means you're finding the member of that family with the smallest KL divergence from the true distribution. So we and they both do this. One example would be, well, I know that there are lots of correlations, but what's the best product distribution? What's the best distribution where the spins are independent of each other? And that corresponds to a very simple type of mean field calculation.
Yeah.
The belief propagation is sort of the next level up in a hierarchy of cluster expansions, if you will, because it does take nearest neighbor correlations into account.
Yes.
And then when you go beyond that, you get to this Kikuchi hierarchy and so on. So there are lots of subtleties, especially in making it rigorous. But so I think in computer science, it was Judea-Pearl. That slightly preceded the use of it by a couple of years in spin glass theory. But of course, the beta approximation, where we
Yes.
pretend that lattices are trees,
Yes.
and on that basis, calculate macroscopic quantities, goes back much earlier.
Yes.
So even now, I think the polite thing to say when you're around computer scientists is that the cavity method is a technique for doing macroscopic calculations, and belief propagation is an algorithm you can run on specific finite graphs. But of course, it's the same idea.
Yeah.
And yeah.
Great. Anyone has any questions? I had several others, but I won't hog the scene, and if anyone else has any questions, to ask first. Yes, Fawad. Go ahead.
Yeah. Hi, Chris. Thanks for a very interesting talk. So
Thanks.
I'm asking a question that may not actually make any sense because it's very, very imprecise. So in physics, often, of course, we use the big data to infer the correctness of various models, for example. And often the situation is very similar to what you described, that you can have a curve with large number of parameters that fits very well in complete data, but then it differs appreciably from the correct data set, basically.
Right.
While a model which is not very precise for the complete data actually works better. So
Right.
in physics, of course, that often happens, and there the criteria generically is that you can cook up lots of crazy models that fit data very well. On the other hand, the model that we know is preferred is the one which is mathematically consistent. So there are these overall consistency conditions that do not at all enter at the level of fitting to data, but they enter from when you look at other considerations, like is your theory consistent mathematically with other theories? Does it fit with, does it work at high energies? Is it consistent with some other quantum system that all those kind of things,
Right.
which do not come into play when you are just looking at fitting the data set that you have. So is there, can one think of some method of incorporating these kind of more general considerations into the picture, which do not really have to do with a specific data set one is dealing with?
Yeah, this is a great question, and I have, you can answer it at several different levels, right? I mean, a Bayesian might say, oh, well, take whatever conditions you want and just impose them as a very strong prior on the model space, or simply define your model space so that every model in that space is, set certain coefficients to 0 if they have to be 0, or set them equal if they have to be equal, or positive if they have to be positive. But I think maybe the more interesting point is that there's again this cultural difference where I think in machine learning and data science, there's this sense of, oh, we'll let the data speak for itself, right? But the negative side of that is often, and of course, I'm speaking to the choir here, maybe, that, because I am originally a physicist, then there's not enough thought about mechanism and, as you say, consistency. And I'll take a wonderfully terrible recent example, not from networks or from physics, but from corona. So a few years ago, a high-level group in the government of my nation state was fitting curves to the case data in corona. And there's a standard model in ancient, sort of century-old epidemiology, which basically fits a Gaussian to it. And then somebody said, oh, well, we can make a better model where the log isn't a parabola, it's a cubic. So this will be a more accurate model, right? And it also had the advantage of predicting that the epidemic would be over very soon, which of course was politically useful. And it was kind of shameful because actually one member of this group was some Nobel Prize winning economist. And so for everyone who understood either epidemiology or data, this was extremely amateurish. So as you can imagine, now that you have a third order coefficient, well, one of two things is going to happen. Either it will predict that everyone in the universe will be infected very soon, or that no one at all will be, that there will be 10 to the minus eighth cases. And neither of these were true at all. And so yes, I think the most interesting work is happening at the boundary, where there is a strong sense of mechanism combined with, yes, we have lots of data, yes, it's noisy, yes, we're not sure what's going on, so yes, let's use clever algorithmic and statistical techniques, but let's really try to impose some mechanistic understanding as well. Yeah, so it's probably a longer discussion, but yeah.
Thanks. Yeah, so basically it has to be dynamical. You have to keep going back and forth, looking at the specific applications you have in mind, and then make a good guess, basically, I would say.
Well, and of course, the other difference is that physicists want to understand what's going on, whereas in machine learning, we give ourselves credit simply for prediction, right? And yes, historically, physicists did a lot of experiments and gave ourselves credit for prediction too, but not simply because we want to predict the outcomes of experiment, because we want to understand reality. And so that's, I think we need to keep reminding people that that's the goal.
Great. There was any other questions, anyone? Actually, if I might slip in a couple other questions, and it was, and now I'm asking maybe a little bit technical. I mean, yeah, slightly technical in the sense that is this phase transition happening at what is what we call the solvability transition for these constraint satisfaction problems, or?
Yeah, so that turns out to be a little bit different. So, so what Supriya is referring to is if you have some logical problem where we have a bunch of variables that are true or false, and then we have a bunch of constraints, like one constraint says that either this one is true or that one's false or that one's false. And then another constraint says something similar. And we really want to strictly satisfy all these constraints. So then it's a lot like asking, is there a zero energy state of the spin system, a non-frustrated ground state? And of course, there are phase transitions here as well. And in many cases, these are actually harder to understand than the ones I've been talking about. It turns out that, so what I've been talking about are what's called planted models, where there is a solution, in a sense, right? There is a ground truth. And then what we observe is built in some noisy probabilistic way around that ground truth. And then we're trying to recover it. So it's more like a spin system where first I choose a particular configuration of the spins. I choose which ones are up and which ones are down. I then design a Hamiltonian where the terms of that Hamiltonian are biased to make my chosen state relatively low energy. So, every time where in my chosen state these things are opposite, I put an anti-ferromagnetic bond. Wherever they're the same, I put a ferromagnetic bond. Then, of course, I just show you that Hamiltonian. Okay, and I ask you as a kind of game to find approximately my chosen state. Now, the thing is that my chosen state might not actually be the ground state of that Hamiltonian. Okay. If I put in enough interactions or strong enough interactions, or if I did this at a really low temperature, then it would be the ground state. But actually, I did this in a probabilistic way. I just said, okay, if these things are opposite, then 2/3 of the time I'll make this anti-ferromagnetic, and 1/3 of the time I'll make it ferromagnetic. Or I'll have some Gaussian coupling there with some bias. So one way to put this is that I'm nature. I'm trying to send you my chosen state, but I'm sending it through a kind of noisy channel. And you might not get the message, right? The message might not come through. And your ability to recover the message might depend not just on the actual thermodynamics of this Hamiltonian I've sent you, but it also might depend on things like glassiness and free energy barriers. So there are several possibilities. It could be that the true ground state is very close to my chosen state, which is also called the quote planted state. It could be that the true equilibrium is not biased toward it. It could be that it is, but that it's hidden behind an energy barrier and it takes you a long time to find it. So that's sort of what's going on.
That's
so,
the conclusion he got here.
Yeah. One interesting fact for replica symmetry buffs is that in these planted models, if you happen to know the parameters, such the quote temperature at which they were generated, at which the network or the Hamiltonian was produced, so that you also know the temperature at which the hidden state is sort of drawn retroactively, if you know what I mean, then there's no thermodynamic replica symmetry breaking. There's no, quote, static replica symmetry breaking. There can be dynamic replica symmetry breaking. There can be loss of ergodicity and free energy barriers and all that. On the other hand, in these constraint satisfactions you're describing, there can be all sorts of full Parisi style replica symmetry breaking, and things can be very difficult to understand.
I see.
So,
but and I think maybe one so I should ask again, did anyone else have any questions? Otherwise I had one more question and then we'd probably need to let you go.
I have my whole day in front of me.
Yeah, but you got up early, so maybe you need to get a little bit of sleep first.
It's not quite that bad.
Okay. Yeah, so
the sun is up.
Yeah. So no, I had actually one question about, if you actually got a network, and you were supposed to, you don't know which side of this transition it's on. You just got some bunch of points connected to each other. How would you know? You don't have any order parameter or anything, right? How would you know where it's lying in this?
Right. Well, two things. One is I feel obligated to say, since I'm a theorist, I think most of the networks people look at, the structure is fairly strong, like in that network of blogs. It's also true that in most real network data sets, we know much more than just the topology, right? Like I was talking with a friend of mine who studies protein interaction networks, and I sort of said, oh, let's work on this. And he said, I'd be happy to, but we actually know which proteins are hydrophobic and which ones are hydrophilic, and that alone gives us a lot of information. And which we know which bacteria like high pH and which ones like low pH, and that alone gives us a lot of information. So I think in most real scientific contexts, it's a little bit more like that graph I showed you briefly, where we have some, quote, metadata about the nodes.
So you have some labels, the nodes have some labels that you can guess or something.
You have some labels, yeah. So I think in practice, you can always reject the completely null hypothesis that this is a purely random graph, right? On the other hand, there are some nice recent papers that say, yes, but in practice, when you run the standard algorithms, there are often many competing community structures that look equally good that don't look very much like each other. So, or there might be agreement about a big clump over here, but then a lot of disagreement about a kind of mixture over there.
Yeah.
So I think the theory is helpful sometimes, even in the real world. To answer your question, a standard technique is cross-validation. So what I would do is, if I'm trying to figure out whether a network or a data set has perceptible structure, well, what I most wish I could do is reveal more of it in the future and see if the structure I found here helps me predict what I'm learning there.
Right.
But if that's not available to me, I kind of simulate that by hiding part of this data from you. For instance, erasing 10% of the edges or adding some additional edges which aren't really there. And then seeing if the algorithm can predict some of those missing edges, predicts the so-called link prediction problem, or identify which edges are not really there. And if you can do that fairly well, it means you figured something out.
Yeah.
So yeah, this has a million names. I think it's been rediscovered a million times. Dividing your data into a training set and a test set, and then doing that many times, okay, we'll hide this part, see if we can get it back. We'll hide this part and see if we can get it back, and so on. And so I think that's one good way to do it.
But the only problem with that way is that if you get the clustering and, then okay, fine, you had the information. If you don't get it, then, you can't say anything. You might just have the wrong algorithm or whatever. Yeah.
You might have the wrong algorithm. You might have the wrong model about how the clustering affects the edges. Of course, it's also good to think about, well, why are we doing this anyway, right? So in the model I gave you, everybody belonged to one and only one group. But of course, that's not true in any real network. Groups overlap. People belong to them with different levels of affiliation. Some people are peripheral members. Some people are central members who are totally devoted and only connect to others in that group. So, stepping back, probably the best scientific answer is that the most appropriate clustering of the network is actually an application-dependent thing. Are you trying to predict some kind of dynamics like an epidemic or flows of current on a power grid? Or is there actually some attribute of the nodes that you're trying to guess, but which you could later go and check on? Are we in a situation where first I only have the topology and then later on I gain the ability to measure something about the nodes, then I can check to see whether that new information is correlated with the clustering I had? So, going back a little bit to Fawad's question, in real networks are very noisy things, right? We don't necessarily even agree about what the links are. In an online social network, I link to you, period. But even there are multiple kinds of links. People study Twitter, and they want to know, oh, should we use the direct messages as the links or the retweets as the links? In a food web, we might get different answers if we just use predation, this species eats that one, but we might get different answers if we look at symbioses. And there's a controversy about whether parasites should count as predators, and in a genetic regulatory network or in brain networks, right, from fMRI data, are we going to try to really find physical connections between things? Or are we just going to look for correlations and then try to infer from those correlations which things are connected? So, whenever you kind of scratch the surface in the world of networks, you find that there are many scientific choices being made about how we define the links and the nodes and what we're hoping to discover. And so it means kind of taking off the theorist hat and moving away from the beautiful math. But, if you really want to say something about biology or sociology, then you kind of have to get more into the weeds there.
Yeah, so that's truly a sort of complex system. Yeah.
So, as they say, yes.
As they say, yeah. Well, any other questions, anyone? Any questions, comments? Otherwise, I think it's really time for us to let you go, Chris. And I really hope that we will get to see you. You had a lot to tell us. You gave us some tantalizing slides there.
I'm sorry. There's the rule: no matter how many slides you skip, you didn't skip enough slides. So
no,
anyway.
You kept perfect timing, just perfect, I think. But there's a lot behind. We see there's a lot more. So we hope to see you in Stockholm, if
that would be
putting
lovely.
this pandemic behind us and when traveling is possible again and so on. So
well, I still have family in Copenhagen, so then I can just hop on a train or a ferry.
yes, indeed, it's not far at all. Yeah.
Yeah.
Okay.
All right.
So thank you and have a great day.